Hello everyone, Mr. Fawcett here, and we are back with another geometry lesson. Today we're going to take a trip over to the physics sector, and not that we're not going to be doing geometry, but it just has a lot of overlap with a physics course, whether you've taken one already or whether you're planning on taking one next year, etc. This lesson is a little introduction to a pretty big concept that you'll talk about when you do take physics, and that is vectors. So let's just jump right in. We're going to skip the do now. There's quite a bit to do in the lesson today, so the video might go a little bit longer than usual. But let's just jump right into the vocab. So a vector is a quantity that has both a length and another word for length is magnitude. So it has a length or a magnitude and a direction. So in physics, you'll hear another vocab word called a scalar quantity. So a scalar is a quantity that just has a magnitude. So a scalar would be like saying I traveled 55 miles in my car yesterday. A vector would mean that you have to add a direction component to that scalar. So you could say I traveled 55 miles east. Now you've made it a vector because you have a distance or a magnitude or a length, and you've told someone in what direction you traveled. In geometry, you could think of a vector as a line segment that has a direction. So it has to be a segment, right? Because if you have a line, well, that doesn't have a length, right? That has an infinite length, but you can't measure it. So if we have a segment and you tell someone which direction on that segment you're going, so if we talk about this segment right here, if you say you go from A to B, well, now you've made it a vector because you've given someone a direction to travel on that segment. A couple different ways you can name a vector. Sometimes they'll give you a little letter out here to name the vector by, so you could just say vector V, and you have that, it's like the top half of an arrow on top of the letter. That is vector notation. Or you can name the vector using the initial point and the terminal point. The initial point being where you start and the terminal point being where you end. And it is important that the terminal point comes first. So we could do vector A, B. Technically, yes, you could do, or write it like this rather, but you would still say vector AB, right? Because A is your initial point, and that's what you would start by saying. It's kind of like array, right? If I'm naming array, I could say array AB. If I wrote it this way, I would still call it, though, ray AB. I wouldn't call it ray BA, because you're going to start with the initial point. You can also name a vector by its components. This is called component form. Here we use these little arrows. Oops, let me get my pen out that they're using right here. X is the horizontal change. And Y is the vertical change between your initial point and your terminal point. So if we take a look at this vector over here, vector CD, well, yes, you could call it vector CD, or you could just name it using the components, right? So 2, 3. Because to go from C to D, you're traveling two units horizontally, and you're traveling 3 units vertically. Notice that there is a direction with those numbers, right? Because positive 2 means you're traveling to the right. Positive 3 means you're traveling upwards. If you wanted to tell someone you were traveling to the left or down, then you would use a negative sign for those. So these are just the different ways you can name vectors. Let's now talk about how to find them. And I think we're also going to do some practice with naming as well. Yeah, we are going to do one practice problem with naming first. So take a look at the vector on the graph over there and try to name it as many different ways as possible. You can also do number 2 as well. This time they don't give you a visual, but they give you the initial point and the terminal point. So pause the video, take some time to name those as many different ways, and then we will move on. All right, so our vector on the plane over there, well, we could name it vector EF. And I'm not going to talk about naming it the other way, right? Because this really means the same thing, and you're really never going to see this notation, right? They're always going to stick with this one. So we can say vector EF, or we can name it using component form. So my x, or my change in x, always comes first, and to go from E to F, I'm going positive 4 units in the x direction, and I'm traveling negative 3 units in the y direction, or 3 units down. So that would be the only two ways, those would be the only two ways to name that vector up there. For number 2, again, first way I could do it would be to name it with my starting point, so P, and then my terminal point, so vector PQ. Or I could name it in component form. To go from 7 to 4, right, well, I can just use some subtraction there. And you have to be careful, right, because I'm actually traveling to the left here to go from 7 to 4 on the x-axis. So you're really doing 4 minus 7. And maybe I'll actually write this out. So 4 minus 7 and 3 minus negative 5. So component form would look like negative 3, positive 8. Because you're going to be adding 8 to negative 5 to go to 3, and subtracting 3 from 7 to go to 4. All right, let's get into the more interesting stuff, which is talking about the magnitude and direction of vectors. Like we said, the magnitude of a vector is its length. This can be found using the Pythagorean theorem. I'm just going to type that out, actually. So we can use the Pythagorean theorem or the distance formula. Remember, those two are very closely related. The direction of a vector is the angle that it makes with the horizontal. Talk a little bit more about how we find that in a second. But the direction of the vector is the angle that it makes with the horizontal. And we start measuring in the counterclockwise direction. So if I take a look at this vector right here, I can't find the distance, or I can't find the magnitude of the vector because I have no, numbers. I don't know the initial point, the terminal point, or any of the components. But what they do give us is the direction of the vector. So again, when you're finding the direction of the vector, you start with the horizontal. Right? The horizontal is the same, whichever way you're drawing it. And then you're taking a look at that angle in the counterclockwise direction, right? This is going counterclockwise. So the angle between the vector and the horizontal is going to be the direction of the vector. Okay. We can also give directions, or we can also we can also give the direction of the vector using compass directions. And let me scroll down here. But essentially, compass directions meaning north, south, east, and west, which for some people is more useful than just, actually probably for most people, north, south, east, and west is a lot of times more useful than, saying 56 degrees or 138 degrees, etc. So what we do here, if I'm trying to describe this vector over here, and I am given that angle, well, there's a couple different ways we could name this. We could say that the vector's traveling north, but it's being pulled off to the east by 30 degrees. So that's where this north 30 degrees east comes from, right? It's traveling north, but not exactly north. It's being pulled off 30 degrees to the east. Now let's say, and you can actually pause the video and think about this, is there some other way you could try to name this? What if you thought of the vector traveling east, but being pulled off to the north by a certain amount of degrees? So I'll just give you a hint. East, something north. Could you fill that in for another way to describe how this vector is traveling? Well, if that angle up there is 30, this angle right here has got to be 60, right? Because the entire quadrant is 90 degrees. So you could also describe the vector as traveling east, but being pulled off to the north by 60 degrees. And those are the only two that you would give, right? You could, if it's in that quadrant, you could either start with east or you could either start with north. You would not start with south. You would not start with west. So either east or north. So there's two different ways. All right. We've talked about how to name a vector. We've talked about how to find the magnitude or the length. And we've talked about how to at least you describe the direction. Now let's actually, learn how to put all of that together in a single problem. So we have a vector that's given by 4, 6. Those are the component forms. We need to find the magnitude and direction to the nearest tenth. We're also going to sketch it on the coordinate plane. We can assume that the initial point is the origin. And for all the problems we do in class, whenever we're given just a single vector, we will probably assume that the initial point is the origin. Not always the case, if you are taking a physics course, but, for our basic introductory lesson to vectors, that's what we're going to assume. So first thing I'm going to do is I'm going to draw it. If I start at the origin, so there's my initial point, and I travel 4 on the x-axis and 6 on the y-axis, my ending point or my terminal point is going to be up there. So my vector is going to look like that. It's always good to put a little arrow there to show which way you're traveling, right? If you just put the segment, then people aren't sure, well, are you traveling away from the origin or to the origin? We've already named the vector, right? That was given to us in the problem. So now we need to find the magnitude and the direction. I'm going to start with the magnitude. So can we figure out the length of that vector? I'd encourage you to pause the video. We know how to do that given previous lessons, and we'd already talked about a little bit above how to do that, so give it a shot. Okay, a couple ways we could do this. We could use the distance formula, or we could just create this right triangle, which is what I'm going to do here. I think it's easier to explain. And I know the two sides of my right triangle are 4 and 6. So easy Pythagorean theorem problem, right? 4 squared plus 6 squared equals, we'll say m squared. We'll just call this side m. So I get 24. I get 16. 16 plus 36 is equal to m squared. 52 is equal to m squared. I'm telling you, one of these videos, I'm going to get through it without having one of those lines jump out at me on the page. Square root of 52 is approximately 7. We're rounding to the nearest tenth, so 7.2. So that is our magnitude. Now we need to find the direction. And I'm going to use compass directions here. So think about which angle I need to find. If I want to give my compass directions, and we're in the first quadrant, so it's going to be, using north and east, think about which angle of that triangle do I need to find. Well, it's going to be this one. So if I'm trying to figure out that angle, think about the trig equation I need to set up. Well, this side would be the opposite. This side would be the adjacent. Yes, you could use the hypotenuse. However, the hypotenuse, we rounded here to 7.2. So unless you were going to use the square root of 52, right, use the exact number in your trig equation, I would just stick with the opposite side and the adjacent, because those are exact answers, whereas 7.2 is a rounded. And if you use a rounded answer, in your equation, then your final answer isn't going to be as exact as it could be. So I'm going to use tangent. Tangent of theta is equal to 6 over 4. I'm going to use some inverse trig. So theta is equal to inverse tan of 6/4. We are rounding to the nearest tenth. So inverse tan of 6/4 is 56.3 approximately. 56.3 degrees. Now, that's not our answer because I'm asking you to use compass directions. If it just said give the direction, that would be sufficient. But I want to go one step further and talk about the compass directions as well. So if I need to use north, east, south, or west, two of those, I think I already told you which two to use, but think about the order, and think about, are there multiple ways to write it, right? So we should be able to come up with two ways to write good compass directions for this vector. Pause the video and see if you can figure that out. Okay, so I can start off by saying I'm traveling east, but being pulled to the north by 56.3 degrees. So east, 56.3 degrees north. Now I could also think about this as starting off going north, but being pulled, whatever this angle is, we'll call that alpha, being pulled by that much to the east. We should be able to figure out what alpha is, right? Because alpha plus theta should equal 90. So alpha plus 56.3 equals 90, which means alpha is equal to 33.7. It is approximate because 56.3 was approximate. So we could also say north 33.7 degrees east. So three different ways you could describe the direction of this vector. One, just with the angle, and that would be if they didn't ask for compass directions. If they did ask for compass directions, then you have your choice of either orange or brown down below. All right, we do have one more example. We got to talk about when we have more than one vector. And this would be when we are adding two different vectors together. And we have this method called the head to tail method. So here we have two vectors, u and v. So that's not going to use brown for that color. So I would travel along u, and then wherever I ended up at the end of u, that is where I would start my vector v. So when you're adding two vectors together, your terminal point of the first vector ends up being your initial point of the second vector. And it doesn't matter which order you add the vectors in. Notice that if we had started with vector v, well, we would have started going up here, right? And then we would have done vector u, and we still would have ended up at the same spot. So, and we call this the resultant vector. The new vector that's created, the vector that would be the shortest distance from the initial point to the final terminal point, we call that the resultant vector. Algebraically, all we have to do is add the different components together to figure out what the resultant vector is. So again, generalizing this, I'm going to add my two x values together. So x1 plus x2, the x value from the first vector, or not the x value, but the change in x, how far I'm traveling, and in what direction from both vectors. I add that together, and then I add the y components together. And that would be my resultant vector. So this just complicates our problems a little bit more. We may have to create some right triangles. We may have multiple triangles to work with, but let's take a look at one below, where we have to sketch a diagram and also find the magnitude and direction like we did above. I do recommend for some of these problems you have like different colored pencils or pens, just because when you have a bunch of different segments and things you need to label in a diagram, sometimes a single color can not make it pop out to you and not help you see the relationships as much. So a couple colored pencils might help you if you're a visual person. So it says a kayaker leaves shore at a bearing of north 55 degree east and paddles at a constant speed of 3 miles per hour. So that's our first vector. We have a direction and we have a magnitude, 3 miles per hour. There is a 1 mile per hour current moving due east. So we need to figure out what are the kayak's actual speed and direction. Round the speed to the nearest tenth and the direction to the nearest degree. Draw a diagram to model the scenario. So let's first start by sketching that first vector. So it says we are traveling north 55 degrees east. So my initial point is going to be at the origin. And I'm going to be coming off somewhere. Let me get my straight line here. I'll be coming off something like here. And the magnitude here is 3 because it's 3 miles per hour. Let me also label the degree as well. This angle right here, because I traveled north and then I was pulled off to the east by 55 degrees. So that angle right there is 55. The next vector is the 1 mile an hour current moving due east. So that is strictly a vector. We'll do this one in blue. We can start my point, my initial point where the terminal point of my first vector was, and again, that's going east. And that magnitude is 1. So what I'm looking for is my resultant vector, which is going to go from my first initial point to my second terminal point. So I'm trying to find this magnitude right here, as well as state the direction that that vector is going in. And you could think about that, right? If the kayaker, he starts traveling along the pink line, but he's constantly being pushed to the east. Well, his actual path is going to look more like that orange line than the pink line. When I say line, I mean vector or segment. So you'll notice we don't have any right triangles here, at least not sketched in. So yes, you could try to maybe use the law of cosines, the law of sine. The problem is we don't even have enough info for that, because for that triangle that I have drawn there, I only know 2 pieces of it. I only know 2 sides, and I need to know at least all 3 sides, or at least one other angle to use the law of cosines or the law of sines. So what we're going to have to do is sketch some right triangles in here. The first one that I'm going to sketch is this right here. I'm going to make this a right triangle. You know what? Let me just do this whole thing in red. Whoops, not my eraser. So let's do a right triangle in red. Goodness, it'd be harder than I thought. There we go. And we're going to try to figure out the pieces of the red triangle. you'll notice here, if I can figure out some pieces of the red triangle, then I may be able to figure out some pieces of the orange. And I would encourage you, if you want to pause the video here and see if you're able to, figure out the missing pieces on your own and eventually figure out the length of that orange segment, go right ahead, because you're going to have to do this for another problem on your own anyway. So if you have a little inkling of where to go, feel free to pause and then come back later. What I'm going to do first, though, is try to figure out this side x, and then I can also go ahead and figure out y down there. Those variables are arbitrary. You can use whatever ones you want. What I do know is that if this angle is 55, then this angle right here has got to be 35, right? If those two together have to add to 90. So I'm going to first use sine. So I'm going to have, sine of 35 degrees is equal to x over 3, which means 3 times sine of 35 is equal to x. 3 times sine of 35, that's approximately 1.721. I'm just going to go to 3 decimal places in the middle of my problem. At the end of the problem, I think it says nearest tenth for magnitude. So I know that x is 1.71. And let's do y. A couple different ways to do y. You could use Pythagorean theorem, or you could use another trig equation, which is what I'm going to do. Cosine of 35 is equal to y over 3. So 3 times cosine of 35 is equal to y, which means that y is approximately 2.457. Make that 4 a little better. Okay, so figuring out the pieces of the red triangle now allows me to figure out the orange because I know the pieces of this green right triangle. And let's think about it. Well, the height of the red is the same as the height of the green. Height of the red was 1.721, approximately. Height of the green is 1.721. If I think about the base of the green, well, that's y plus 1. So that ends up giving me 3.457. And now I can use the Pythagorean theorem to figure out m. So 1.721 squared plus 3.457 squared, that's going to be equal to m squared. I'm not going to write out all the math here. I'm just going to do it on the calculator and put it down. That gives me approximately 3.9 for m. And our magnitude here is a speed, so it's miles per hour. So m is approximately 3.9 miles per hour. That's the actual magnitude between how fast he's paddling and the current. Now we still need to find a direction. Again, diagram's getting a little cluttered, but that's why I encourage you to have multiple colored pencils here. The angle that I want to find is this angle right here. It's not the 35-degree angle. It's part of the 35-degree angle, so it should be a little less. So it's that angle in the green triangle. To do that, we are going to use inverse trig. So I'll first set up a regular trig equation. And I'll just do tangent. You know all three sides, so you could do whatever one you want. So tangent opposite over adjacent, 1.721 over 3.457. That means that theta is equal to the inverse tan of that ratio. And we are rounding the direction, it looks like, to the nearest degree. Which ends up being 26 degrees approximately. So if they just wanted the direction and didn't say compass direction, that would be sufficient. However, I'm going to ask you to think about the compass directions as well. So again, two choices here because it's in the first quadrant. We can go north something east or east something north. This angle, this would be east 26 degrees north. That's one possibility. Or I could think about starting off going north and being pulled in the eastern direction by 64 degrees. Again, just 90 minus 26 would be 64. All right, so this is about as complicated as it gets for the vector problems we'll do in this class. Feel free to work on the other ones in this packet if you want, although you will have some time to do them in class. We are going to end the video here. As always, enjoy the rest of your day, and I think next time we're back on, we will see everyone for a new unit.